this video, we will be looking at exponential decay. So we're going to start off with an example where we create a table of values, do a sketch, try to figure out how the equation will relate to exponential functions. So antibiotics kill bacteria. Some kill bacteria by destroying the bacterial cell wall, others by interfering with the bacteria's ability to reproduce. Let's take a culture of 80,000 bacteria. When an antibiotic is introduced, 10% of the bacteria is killed every hour. This means every hour a certain percentage remains. So if 10% is lost, the leftover from 100% should remain. So when we subtract 10 from 100%, we're left with 90%. So that means hour to hour, the bacteria culture will retain 90% of its numbers. To find the number of remaining bacteria, we multiply the number of bacteria by 0.9, and that's supposed to be 90%, because whenever we want to take a percentage of a number, we take that number and multiply it by the percentage when the percentage has been divided by 100. So let's continue this pattern and complete the table. So after an hour has passed, we need to multiply 80,000 by 0.9, and we get 72,000 bacteria. Now I'm going to take this number that has already been multiplied by 0.9 once and multiply it by 0.9 a second time, and that's going to take us to 64,800. Then I multiply by 0.9 for the third time. That takes us to 58,320. Multiply again. 52,488. Again, 47,239. And one more time, 42,515. And now, I can do my sketch, I can do my ratio. Now, because I did already specify that this is an exponential model, I am expecting a common ratio. But as a reminder, we're going to divide the bottom number by the top number. And when I do that, I get 0.9. The 47,000 divided by the 52,000-ish, and we get 0.9. And I keep dividing, and I should get 0.9 each time, which matches that multiplication number. Let's do a quick little sketch. So I'm going to have number of bacteria on my y-axis and number of hours on my x-axis. Now I'm starting at the maximum number of bacteria on day 0, which is 80,000, and then from there it is just dropping. I can add a little bit of accuracy if I wanted to by plotting some of these points and, let's say, labeling this one here as 2 hours later. The population is 64,800, but this is going to be the general shape. Now, logically, and based on what we know about exponential functions, this will not drop below the x-axis because there's an asymptote there. Logically, it doesn't make sense for me to have a negative number of bacteria. And I mean, in reality, we would get to 0 bacteria, but mathematically, it would be 0.0000, something really tiny. Let's write a function to represent this relationship. X is going to be the number of hours, Y is going to represent the number of bacteria. So we started off with 80,000 bacteria, and we multiplied that number by 0.9 a certain number of times. After the first hour, we multiplied by 0.9 once. By the second time, we had multiplied by 0.9 again, which made it 2 times. So by hour 2, 80,000 was multiplied by 0.9 2 times. By hour 3, it was multiplied 3 times, and so on. So if x hours have passed, it's going to be 0.9 to the power of x, meaning 0.9 was multiplied by itself x times. Now, in terms of our domain and range, state the domain and range of this relationship, assuming the bacterial culture is wiped out after a day. So a day, we know, is 24 hours, and I need hours because my x-axis is about hours, not days. So my domain is from hour 0 to hour 24. My range, I know the highest amount, I know my upper limit of my range is 80,000, but my bottom limit, we're not actually going to reach 0 necessarily, but we're told that the scenario ends after a day. So I'm going to use my equation to see how much bacteria is left after 24 hours. And when I do that, I get approximately 6,381. So that would be the starting number of my range. So it's not wiped out to 0, but it is dropped enough that maybe you don't have symptoms anymore. If the antibiotic was stronger and killed 18% of the bacteria each hour, then how would the graph change? And then how would the equation change? If the antibiotic has a stronger effect, then the drop must be more rapid, which means our graph would look steeper. The equation, the initial value is not changing, but the number inside should change. We got 0.9 because we took 100 and subtracted 10 to get the leftover. So now if the antibiotic is killing 18%, if I take 18% away, we're left with 82%, which means our base should be 0.82. 82% of the bacteria remain from hour to hour, which means we're multiplying 80,000 by 0.82, however many times we need. If the bacteria culture initially had 50,000 bacteria, how would the graph change? Well, it's a smaller population, so our y-intercept would be lower. We'd start lower on the y-axis. And the equation, well, now because the initial amount is changing, it's that starting value that goes from 80,000 to 50,000. And then I'll put my original rate. And there we are. So if we compare this to what we saw for exponential growth, the only difference in the equation is that now your base is less than 1, so that our numbers are decreasing from time to time. So let's generalize that. Now, we looked at a decay by a percentage. That should say decay there. So we still have our A value being the initial amount. We still have the same exponent as with growth, where we have a fraction where the numerator is the total time and the denominator is the decay period, so how often that decay percentage occurs. But inside, because we want it to be decay, we're going to take 1, which is mimicking 100%, and subtracting that rate from it. Now we also have a very specific factor example. So with growth, we had seen doubling, tripling, quadrupling, etc. For decay, we could have our amount being cut in half or a third. So a very specific one is half-life, and that's when you have an original amount and it takes a certain number of days, hours, years, whatever it might be, for that amount to be cut in half. So for the rate, we use a half or 0.5. So our first example, the value of a car depreciates over time. The function v at t equals 58,000 times 0.68 to the power of t over 2 models the value of the car v after t years. Explain the meaning of each part of the equation. Well, this is going to tell us that the car's value was $58,000 originally. Our rate here is every 2 years because it's t over 2. And to figure out the actual decay rate, I'm going to take 1 and subtract 0.68 because the 6.8 represents the car maintains 68% of its value. So if we want to know the decay amount, we have to do that subtraction, and we'll get 0.32, which means 32% decay or 32% loss every 2 years. All right, next example. A radioactive substance has a half-life of 5 years. Initially, there are 100 milligrams of this substance. Okay, we're dealing with mass and we're dealing with years. So I'm going to say let m represent mass in milligrams. Let t represent time, and it's in years. So our initial mass was 100. Our rate is half. and we cut in half every 5 years, so t over 5. How much substance is left after 100 years? Well, I want to evaluate m at 100, which means 100 times half to the power of 100 over 5. And 100 over 5 is 20, so that means that our substance is going to lose half of its amount 20 times. So now I'm going to punch this into my calculator, and my calculator gives me approximately 9.5 times 10 to the negative 5. Like, this is what your calculator might show. If you want to write that without this scientific notation, the fact that this exponent is negative means we have to move our decimal to the left, and we're going to move the decimal to the left 5 times. So 1, 2, 3, 4, 5. This is where my decimal should end up, and the rest should be zeros. So 0.1234 zeros, and then 95 milligrams. So therefore, in 100 years, 0.000095 milligrams remain. All right, when will there be 6.25 milligrams left? So now we're given the mass. So 6.25 equals our equation. Now, we know from solving exponential equations, if there's a coefficient, we should divide it out. Depending on your calculator might give you this decimal, and then a half is just 0.5, so you can write it like that. And then you'd be using kind of a guess and check strategy where you're trying to figure out 0.5 to the power of what gives you 0.0625, because you're trying to match to the base with the variable. Or some calculators, or if you know the decimal off the top of your head, will give you 1 over 16. And if you get that, that avoids the guess and check, because 16 can be written as 2 to the power of 4, which means 1 over 16 can be written as a half to the power of 4. And now that my bases match, I can set the exponents equal to each other. So 4 equals t over 5. And then when we put the 4 over 1 and cross multiply, we get t equals 20. So therefore, in 20 years, 6.25 milligrams remain. So that's a half-life example. The solving process is nothing new compared to when we had growth the other day. Final one. A ball is dropped from a height of 5 meters. Each time it bounces, its height decreases by 20%. How high does the ball get on its 6th bounce? Well, first of all, I need an equation. So we're dealing with height, and we're dealing with number of bounces. So I'm going to say let h represent height in meters, let b represent number of bounces. So the original height was 5, and each time it bounces, it loses 20% of its height, which means from 100, if we lose 20, we're left with 80%. 80% remains, which means our base is going to be 0.8 in our equation, and it loses that height every bounce. So just going to the power of b is enough because it's every 1 bounce. If it was every 2 bounces, I would do b over 2. And now if I want to know the height on its 6th bounce, I will do h at 6, which is 5 times 0.8 to the power of 6. And I get approximately 1.31. So therefore, on the 6th bounce, the ball is approximately 1.31 meters high. All right, last one. Predict which bounce will result in a height of approximately 0.5 meters. So now we're given height. So 0.5 equals 5 times 0.8, to the power of b. Just like before, we need to divide out that 5, and I'm going to get 0.1 equals 0.8. Unfortunately, there's no nice connection between 0.1 and 0.8, so it does become a bit of a guess and check scenario. I need both of my bases to match up with the 0.8. So I need to figure out 0.8 to the power of what gives me approximately 0.1. And it might just be a bit of a guess and check at the beginning. So I might try 0.8 to the power of 5. And I got 0.3. That's not good enough. 0.8 to the power of 8. 0.16. Okay, I'm getting lower. I want to be even lower. Maybe to the power of 10. I got 0.107. That sounds good. Let me just try 0.8 to the power of 11. And now that took me 0.085. So I think 0.8 to the power of 10 is best because it gives us approximately 0.107. So it's very close. So now I can rewrite this 0.1 as 0.8 to the power of 10 is equal to approximately to 0.8 to the power of b. The bases match. I can set my exponents equal to each other, still rounding, and then I can say, therefore, on the 10th bounce, the ball will be approximately 0.5 meters high. And that's it for exponential decay. Very similar to growth, same algebra skills. The only difference is when you're given that percentage, you're subtracting it from 100 to see how much of the original value retains from decay period to decay period.